All right, we'll get started. And what I want to do today is continue our discussion on when it makes sense to do certain kinds of integrals, and just sort of looking at line integrals in general, especially line integrals of vector fields, because at this point we know a couple different ways of doing that. So there are a couple different ways. First of all, I just want to remind everyone, I talked about this a bit last week, but I want to remind everyone about some the important principles of integration. And so far, the only thing that there are really only two that we can make serious use out of at this point. And so the principles of integration. And the first of them we talked about before is this issue of syntax. And when I say syntax, what I mean by that is you have to dot vectors with vectors. And and scalar functions with scalar differentials. Etc. Basically, you have to treat your integral as something that makes, that should make mathematically speaking, grammatical sense. The second issue basically involves the differential. Whatever your differential measurement is, it should describe the region / curve, whatever the case may be, that you're integrating over. And what I mean by that is, if you take, for example, this line integral of f dot dr over this curve C, dr in this case is displacement, which is another way of saying length with direction. And if you think about something as length, or especially length with direction, that describes a curve. Curves have length. Versus, for example, something like the double integral over some region D of some scalar function fxy dA. Well, dA, this is area, and D is a region in the plane. And that has area. So whatever the thing is that you're integrating over, it should describe a region or curve. Whatever your differential measurement should describe your region or your curve. So the last example of this that we've really seen so far is a triple integral dV. And in this case, we're looking at volume, and you're integrating over a solid region. And of course, a solid region has volume. So these are the two most important principles of integration. And if you adhere to these principles, then mostly you should be okay. There are two more principles that we haven't really gotten to yet because we haven't talked about surface integrals, but these are the two, really, in my opinion, these are the first two really important things that we're looking at so far. Okay, so I want to do some concrete examples with this. Oh, come on. But before I do concrete examples, I want to remind everyone about the different formulas for vector field integrals that we've seen so far. And there are really three formulas that we've seen. The first one is the direct formula. In the direct formula, your integral over c of f dot dr is just the integral from a to b of f of r of t dot r prime t dt. That's the direct formula. The second formula involves removing an integral. And when I say removing an integral, what I mean by this is you take your vector field integral, f dot d r, and that equals to little f of, I'm going to call it cd, minus little f of, actually, I take it back. I'm going to call it something else. Little f at the end to make it possibly three-dimensional, minus little f at the start. And of course, we recognize this as the fundamental theorem of line integrals. But I'm calling it a removing an integral formula for a very specific reason, because we're going to see other examples of removing integrals in other in other kinds of integration that we'll look at. But this is the first example that we're seeing of this. One option is for removing an integral, but importantly, you can only do this if your vector field is the gradient of a scalar function. In other words, if your vector field is a kind of derivative. The last approach is by adding an integral. And this is what we looked at this week. F dot dr is the same thing as the double integral over d of del q del x minus del p del y dA. Now, a couple things implicit in this formula. For one thing, this is only true if C is in R2, if this is a two-dimensional scenario. And what's D? D is the region enclosed by C. It's the region enclosed by C. And what that means specifically is that C must be closed. So now the reason I want to emphasize this is, in particular, not only does this formula not apply, not only can you not use it if C is not closed, or more particularly, not only is it not true if C is not closed, it doesn't even make sense if C is not closed. What's D? If C is not closed, there's no region that C can enclose. So the right-hand side of this formula doesn't even make any sense in this case. So whatever you're doing here, C had better be a closed curve, otherwise this theorem doesn't make any sense. And this is what we learned this week is known as Green's theorem. So these are the formulas that we've seen so far that can help us in how to take care of different kinds of integrals. And I want to do some examples of this today so we can see what what we're working on so far. So I'm going to pause for a second. So what if, for example, our function or our vector field is given by the integral over c of x cubed dx plus 2xy dy. And just give me 1 second, sorry. And C is the curve that's the curve that's consisting of these line segments And it's 3 line segments from 0, 0 to 0, 2, 0, 2 to 1, 0, and 1, 0 to 0, 0. Okay? Make sure that I got this right. This, by the way, is coming from a previous exam. This problem comes from a previous exam that's in person at Penn State. So what is this thing? Now, my general modus operandi for these is to always draw a picture. Draw a picture of the scenario. And in this case, we know that our curve goes from 0, 0 to 0, 2, from 0, 2 to 1, 0, from 1, 0 to 0, 0. So in total, our curve looks something like this. And the direction that it's going in, the orientation, in other words, is this way. So from 0, 0 to 0, 2, 0, 2 to 1, 0, 1, 0 to 0, 0. Notice in particular that this curve is oriented, or I can't spell. This curve is oriented clockwise. Which is going to be important. Now, at this point, we have to choose how we're going to go about doing this. By the way, keep in mind that this is the same thing as the integral over c of f dot d. This is literally the exact same thing as the integral over c of f dot dr, where f xy is x cubed I plus 2xy j. It's literally the exact same scenario. It's just written in a slightly different way. Now, with that in mind, we can ask ourselves, okay, so how do you actually go about doing this? So again, we've got 3 options. We can either use the direct approach, or we can try removing or adding an integral. Now, generally speaking, the direct approach is the last resort. We use the direct approach if we can't use one of these other more clever, a little bit slicker ways of doing this. So can we remove an integral? So this is this idea that if you take the integral of the derivative of a function, aka the gradient dot dr, that's just f of the end minus f of the start. So can we do this? If we can do this, then this ends up going to be a very easy problem because in this case, the end and the start are the same thing. So this would be 0. So in principle, we might be able to if we can show that, f, our vector field, is the gradient of some function. But is it? Well, in particular, we can ask ourselves if del p del y is the same thing as del q del x. Well, del p del y is 0, right? Because this differentiating x cubed with respect to y, which is 0. And del q del x is 2y. So no, you can't find an anti-gradient. We're not going to be able to use this, this theorem. Let's try. So that's our first strategy. So that's not going to work. Let's try our second strategy, which is adding an integral. Which we've got f dot dr is the double integral over d of del p del y minus del q del x dA. Now, fortunately, we already know what I'm sorry, I got this backwards. Shame on me. I hope I didn't do that on my previous slide, but I may have. It's del q del x comes first minus del p del y. I got that backwards. which in this case is the double integral over d of 2y dA. And we can only do this if we know what d is. But we can see where d, so now we see the value in drawing it out explicitly. We know what d is. D is this triangular region. So d is the triangular region which in particular is given by all x's and y's, so that we have x is going from 0 to 1, and y is going from 0 to, in this case, it would be to 2 minus 2x, 2 minus 2x, yes. Oh, sorry, I left out something important. Now that makes our lives a lot easier. So let's try doing it that way. So just to remind everyone where we are, we've got our, I'll just redraw the scenario. Now, by the way, we got to be a little bit careful here because, as I pointed out before, this curve is oriented clockwise. And Green's theorem stipulates that this is only true if our curve is oriented counterclockwise. So strictly speaking, this isn't true. We missed something. This is a clockwise oriented, so we have to include an extra negative. And I'll just make this perfectly explicit. Why do we have to include that negative? And we have to include it because the curve is is clockwise, i.e. negatively oriented. So the direction you're traveling along this curve is very important for Green's theorem. But we can go on to solve this. Integral from 0 to 1, integral from 0 to 2 minus 2x of negative 2y dy dx, or integral from 0 to 1 of negative 2 minus 2x squared dx. And just going through it, we get the integral from, just expanding it out completely, integral from 0 to 1, negative 4x squared plus 4x minus 4, 8x minus 4, excuse me. In other words, negative 4/3 plus 4 minus 4, or negative 4/3. So that's our answer. And it has to be negative, and again, we have to include the negative because it's counterclockwise oriented. So beware of the orientation. The orientation will ensure whether or not your final integral, or not your final integral, but whether or not your double integral will have a negative sign out front or not. So beware of that. Okay. So for our next example, again, this comes from a previous exam. This is the integral over c of f dot dr, trying to figure out what this is, where f is the vector field xy squared I plus x squared y plus 2x, j, and c is the square with vertices given by 2, 1, 4, 1, 4, 3, and 2, 3, positively oriented. Again, it's always a good idea to draw a picture to try to get as good an idea as possible of what the scenario is. So in this case, boom, 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 2, 4, 4. So in this case, this would be 2, 1, 4, 1, 4, 3, 2, 3. So our curve looks like this. And it's positively oriented, which means that it's counterclockwise oriented. So this is our curve C. Again, we see that it's closed and it encloses a region. So again, we can try thinking about the removing integral approach. In other words, the fundamental theorem of line integrals. Sorry. But in this case, once again, you have to ask the question, if you're going to do that, is your vector field conservative? Well, in this case, so that's the question, is f equal to the gradient of f, of little f, for some of the little f? Well, del p del y is 2xy, and del q del x is 2xy plus 2. So these aren't equal. So no, you can't use that strategy. What about adding an integral? Can you do that? Well, in this would mean that it's the integral over c of f dot dr. And that's the double integral over d, whatever region c encloses, of del q del x minus del p del y dA. And, well, can you, well, the question is, can you find such a d? So, so does C enclose some region T? And you look at the picture and you say, well, yeah, of course it does. Here's D. D is this region inside of the square. So yes, of course we're good on that front. So, and not only that, but in this case, the integral becomes very easy to solve. It's f dot dr is the double integral over d of del q del x is 2xy plus 2 minus del p del y, or minus 2xy. Or in other words, 2 times the double integral over d of just dA. Or in other words, 2 times the area of d. And the area of d we can see is 4. So this whole thing becomes 2 times 4, or 8. That's it. That's all there is to it. It's a very simple problem, actually, if you can use Green's theorem, or if you think to use Green's theorem. Now, can you do this the direct approach? Do you need to use Green's theorem to do this? Well, no, you can use the direct approach, but the direct approach involves breaking this up into 4 different line integrals, right? Because you get 4 different sides, and you need to do 4 different integrals in order to get what all those 4 sides are. Is it possible? Yes. Is it fun? No, absolutely not. This is a much easier way to do this problem. So I highly recommend becoming familiar with when you can use certain results. It'll make your lives much easier as time goes on. So let's do another example of this. So here we have, let me shuffle some of my tools around a little bit. What about the integral over c of 2x plus sine y dx plus x cosine y dy? And c is the arc of the parabola. Y equals 1 minus x squared from 0, 1 to 1, 0. Now, if you draw the figure for this thing, you can see what this looks like. That parabola in question, 0, 1, 2, 1, 0, it looks something like this. So there's our curve C. Now you might be tempted to say, okay, well, let's do Green's theorem because it looks like it's a Green's theorem kind of integral because you've got one function dx plus another function q dy. That's Green's theorem. No, that is not the case. The fact that the integral is written in this way does not imply that it's Green's theorem. Green's theorem often is written in that way, but that does not mean that because you see an integral written this way, you have to use Green's theorem. Remember, this is just the same thing as the integral of c of f dot dr. So we can't automatically assume we can use Green's theorem. In fact, if we try using Green's theorem, so remember, this is the add integral. The add integral approach this is the adding the integral approach of over d. But the problem is, what's d? D has to be the region that C encloses, but C doesn't enclose a region. So since C doesn't enclose a region, you can't just go ahead and do this. But can you remove an integral? Using the fundamental theorem of line integrals. And yes, you can do that. That you might be able to do because del q del x, if we actually do that, that's going to be cosine of y. And del p del y is cosine y. So that's good. That means that our vector field is in fact conservative. So let's try it out. Let's see if we can actually do that. Well, we know that fxy has to be equal to the integral of 2x plus sine y dx. But that is x squared plus x sine y plus some function g of y. Don't know what g is, but we'll find out soon enough. Fy, meanwhile, for doing that, would become x cosine y plus g prime of y. And we know, because we know what f is, that, or big F anyways, the vector field, that's just x cosine y. So g prime of y is 0. So in other words, we can assume that fxy is x squared plus x sine y. So the integral over C of our vector field, dot dr, that's the same thing as f of the endpoint. The endpoint is 1, 0, minus f of the start point, 0, 1, which is going to come out to 1 sine of 0 is 0, so that's 0, minus 0, because 0 times sine of 1, so the whole thing is just 1. And that's your answer. Now, I want to point out something. I want to point out the wrong thing. I want to point out a common mistake. So don't do this. So here's the common mistake. Again, we have, this is the integral over C of 2x plus sine y dx plus x cosine y dy. And again, C is the arc of the paraboloid, parabola, excuse me, y equals 1 minus x squared from 0, 1 to 1, 0. And what we can say at this point, so with that in mind, what we can say here is, let's see, where were we? So, what was I going to say? Oh, okay, so here's the thing. So you might try to use Green's theorem, in which case this becomes the integral over d of del q del x minus del p del y. But that, sorry, that's a double integral over d. That's the double integral over d of del q del x, which we said is cosine y, minus del p del y, which is again cosine y, dA, which is the double integral over d of 0 dA. And you might say, oh, well, that's 0. No, that is not true. That is not true at all. That is very wrong. And the reason that's very wrong is because you don't know what d is. This doesn't make any sense if you can't talk about whatever this d is that the thing is enclosing. So, now, if you don't know what d is, then you can't actually do this in a reasonable way. This comes out to 0, but we just saw that actually the answer to this problem is 1. The answer to this, this evaluation comes out to be 1. So that's not going to be true at all. The important takeaway here, the important lesson to be learned here, and I'm going to return to this over the course of the remainder of the summer, if you cannot articulate, i.e. verbally describe, if you cannot verbally describe if you cannot verbally describe to yourself the region or the curve or the domain, you're integrating over, then do not integrate. Do not do it if you cannot describe the region that you're integrating over. If you can't describe this thing that you're integrating over, then don't integrate. Probably you're integrating over something that doesn't exist. So whenever you're integrating, make sure you can actually describe fully this thing that you're integrating over. This sounds obvious, but it's really quite impressive the number of times we've seen mistakes in this vein. Don't do this. Don't integrate over something that you can't describe. Don't do it. It's bad, and bad things will happen. Okay, let's do a couple more. Okay, let's do a couple more. So for our next example, we've got the integral over c of f dot dr. We want to know, in this case, f is the function, or the vector field rather. F is the vector field 6x cubed y squared I plus 3y to the fourth, 3x to the fourth yj, and c is the curve y equals x e to the x squared minus 1 plus sine pi x from 0, 0 to 1, 1. Followed by the curve x equals root 1 plus y minus 1 cubed from 1, 1 to 0, 0. Now, I don't know what either of these curves look like. Actually, they're probably quite hideous. So, these are weird curves, and drawing them is going to be a pain. So I'm going to skip that step and hope and pray that this will work out in a nice way. I don't know. This could be quite strange, but let's try it. Let's see. Can we remove an integral? If we remove an integral, this is the integral over c of f dot dr. This is in the case where this is the integral of some gradient vector field Let's see if we can do this. And if we can do that, well, fxy would have to be the antiderivative of 6x cubed y squared dx, which comes out to 3 halves x to the fourth y squared plus some function g of y, which tells us that xy would be the derivative of this thing, which would be 3x to the fourth y plus g prime of y, which we're told in this case is just 3x to the fourth y. So g prime of y is 0. And so we can say that fxy is 6x cubed y squared. Excuse me, I messed it up already. It's 3 halves x to the fourth y squared. So the gradient of little f is the vector field. Now, by the way, nowhere in this stage did we actually calculate the del q del x or del p del y. We could have. There's no reason we didn't, other than we didn't really need to. You don't need to calculate those things to see if it's conservative. You can just try directly to find an anti-gradient, and it might not work out. In this case, it did. We didn't know that it would, and that was a little bit lucky, but if it doesn't, that's okay. Don't panic. Just find a different strategy. That strategy is just not going to work in that case. That's okay. That can happen. That's nothing to lose any sleep over. This is actually very good news for us, because what this means is that the integral over C of f dot dr is, as I pointed out, f of the end minus f of the start. But let's look at our description of the curve. The curve starts at 0, 0, and then goes to 1, 1, and then goes along a different curve from 1, 1 to 0, 0. Which means the end and the start are both the same. In both cases, this is f of 0, 0 minus f of 0, 0. So this is 0. Now, even though I'm not going to draw what the actual curves look like, I will point out that it's going to be something like this, where you have a, here's 1, 1, I want to draw this in blue. Here's 1, 1, here's 0, 0. The first curve is going to be some strange function going up there, and then the second curve is going to be some other sort of weird looking thing from going in this direction, or some straight mark, or something like that. Either way, we can see that it's a closed curve. And do I want to calculate the area of that thing? No, I really don't. However, I do know that this that since it's a closed curve and the function is conservative, we can see now why it has to be the case that this entire function is going to be 0, or why the entire vector field integral is going to be 0 in this case. So that's the good news. This didn't work out too badly at all. All right, I want to do one more. Okay, so the last thing that I wanted to look at, final example. Once again, we're trying to find out what this line integral is, and we're going to say that f xy is the vector field 2x squared plus 3y squared, 3y cubed I plus 3y minus x squared j. And C is the line segment from 1, 0 to 2, 2. All right, so how are we going to do this? Well, again, let's try drawing a picture, and this one is a much easier picture to draw. One thing that I never really learned how to do in graduate school is to draw straight lines. Here's 1, 1. And here's 2, 2. So it's going to look something like this. Well, obviously, that curve doesn't enclose anything, so we're not going to be able to use Green's theorem. But just to drive the point home, I'll write it out anyways. So this is the add integral. And you can't do this because there's no enclosed region D. How about we remove the integral? Do we have a gradient available to us? Well, if we do have such an f, and I'm going to try doing it without calculating del q del x or del p del y. I can tell you right now that it's not going to work, but I want to show you why it doesn't work. So if f exists, then we have to have that fxy is the integral, or the antiderivative of 2x squared plus 3y cubed dx, which is 2/3 x cubed plus 3x y cubed plus some function g of y, which says that fy, xy, would have to be 9xy squared plus g prime of y, which would be 3y minus x squared. Well, that's obviously not true. So that can't possibly work out. So there's no potential function fxy. So we can't add the integral, we can't remove the integral. This leaves us with the direct approach. That's the only thing we can do at this point. Because we can't add an integral because this doesn't enclose a region. We can't remove an integral because this vector field isn't conservative. So we can only use the direct approach in this case, which is fine. We need to parameterize R of t. There's a standard way of doing that. You're starting from 1, 0. It's a line segment, and the line segment is 2 minus 1, 2 minus 0, because it's 2, 2 minus 1, 0. So the whole thing comes out to 1, 0 plus t times 1, 2, or if you prefer, 1 plus t, 2t. So our prime of t is just 1, 2. And if you want to actually go off and do this and plug this in and everything, this is the integral from 0 to 1. Oh, that's the other important thing here, is that this parameterization is for t going from 0 to 1. And I'm just going to set this up because this isn't really difficult to do once you do the algebra. The algebra is just kind of annoying, and I'm being lazy. So once you do this, this comes out to, so x is 1 plus t, so this is 2, 1 plus t squared, plus 3 times 8 is 24 t cubed. I'm going to actually get rid of this other thing there. Comma. 3y minus x squared is 6t minus 1 plus t squared, dotted with the derivative vector 1, 2 dt, or in other words, and go from 0 to 1, 2 times 1 plus t squared minus 2 times, that's actually going to go away, 24 t cubed plus 12 t dt is what that would come out to. Excuse me, no, it was right the first time, it is plus. So in other words, that's 6 plus 6 is 6t squared, differentiate that, so 12. So I did solve it, wasn't that bad. So that's when you know you have to do the direct approach, when you can't enclose a region and the vector field is not conservative. You have to use the direct approach for these planar line integrals. All right, any final questions before I end? If there aren't any questions, then we'll continue tomorrow by looking at parametric surfaces, which is a very difficult topic in this class, and a lot of people have trouble with it, which is fine. We're going to look at some examples of that tomorrow. Bye, everyone.